Hello. This might be a surprising face to run into as you begin this lesson. In fact, as you look at the title of this topic, it says Trig Identities. You might be questioning the identity of the person speaking to you now. My name is Michael Steele. I'm one of the calculus teachers at Franklin, and I volunteered to help out the accelerated teachers because they have a ton on their plate with a bunch of other classes to teach too, and I had already made really good progress on the Calculus BC lessons that I'd been preparing. So I felt like I could help out and pick up a couple lessons here and there and teach those topics to you as best as I could in as expedient a manner as I could. So I am the person who will be delivering the information to you for today's lesson, which is called Trig Identities, as well as the one that will follow, which should be called Simplifying Trig Identities. There may be another one in there somewhere. We'll find out as we kind of go through. I kind of want to get a feel for it one lesson at a time. Having said that, if you don't know me, I run a couple different things on campus. I'm one of the calculus teachers with Mrs. Formaker. I grade AP tests with Mrs. Williams, and I've known Shannon and Ms. Pythagorean for a long time. I coach some athletes team, so I know I've run into a couple of you that way, and also coordinate the Challenge Day program, so maybe a few there too. So again, this isn't a topic that's like my particular favorite topic. It's just one that I felt like I could help out with and that I could help deliver to you in a good, organized way, since I still had my notes from when I taught Honors Pre-Cal a year or two ago. So without further ado, let me just kind of jump into the topic. I don't want to beat around the bush. I'm sure I'll make some bad jokes at some point. You're welcome to laugh. I'll find out if you're laughing and judge you for it if you don't. So having said that, we'll kick things off here. As it says, the name of the lesson is Trig Identities. And the truth is, if that name doesn't speak to you, that's perfectly fine. This is not something you've done before, although all of the algebraic things you've done before and all of the, I'll describe them as trig ratios, are ones that you've used before, but we've never actually brought them together this way. In the simplest way I can put it, and I've been bouncing this idea through my head for a little bit, I would say that the Trig Identities unit, or these couple lessons that we're going to do, are focusing on the relationships that govern all of the trig ratios, and more importantly, how they all connect together. Now, in truth, some of these relationships are going to be ones where you're like, okay, cool, well, I didn't really need that. And you're not going to be wrong, of course. You won't be able to argue with me because I'm going to keep going because I'm recording this ahead of time. Ha! But at the same time, the thing that's nice here is some of these relationships will help us in the future. And in truth, I really believe that this entire Trig Identities unit is simply to prepare you for certain expressions that come up when you're actually taking a calculus course, like the one that many of you will be taking next year, or at the very least, some of you will be taking in the future. So my goal is to prepare you for that. So we're not going to do a ton of intense work. We've kind of cut out the intense verifying section. We'll show you some basics of that at some point here. But we're just going to focus on the relationships. And in particular, in this video, I'm only going to focus on what the relationships are and giving you a single, quick, clean example of that relationship, just so that way you can kind of get a feel for, okay, these are the identities, and these are some ways to remember them or derive them, and of course, I'll also show you some ways to prove them, but they're all going to be geometric proofs. We're not doing anything fancier, and in fact, geometric proof is all we need. We'll draw a triangle, we'll label some stuff, and we'll go, oh, hey, look, that works. So that's kind of our goal here. Assisting me as I work my way through is going to be this, so you're not creeped out by it. If I make a joke that I feel like you should laugh at, I will press this button, and it will provide the laughter. It will provide the laughter for me to fill the gaps, because of course I'm just talking to basically a wall and a computer screen at the same time. So having said that, I mentioned what trig identities really are. Trig identities are the relationships that are going to govern all of the trig ratios and how they connect together. It's not a definition you need to write down. And in fact, this first one that's on the screen right now that many of you may have written down is definitely not one you need to write down either. It's just kind of nice to provide context to the specific vocabulary we're using. So what is an identity? An identity in mathematics is an equation that is always true or valid. So it doesn't matter what values you plug in, it's going to be true and it's going to hold. So obviously some identities are kind of sillier to point out, although this isn't quite the same thing, this is an equation and it's something that holds as well in every system. Obviously there are other bases out there, but we'll talk about them. More relevant is probably one that we've used in pre-calculus at some point, or in the accelerated math course at some point this year. And that is that if you wanted to figure out what secant was equal to, you learned that secant was actually the reciprocal of cosine, meaning that it was 1 over cosine of x. So they were reciprocals of one another. If you knew secant was, let's say, 3 over 2, then that meant cosine had to be 2 over 3. And in fact, that is one of the identities we'll look at today. So having said that, our focus is going to be on determining what we call the fundamental identities. And these are simple identities used to derive or generate other bigger ones. So the truth is, our goal isn't just that you know, for instance, that secant of x is equal to 1 over cosine. Our goal is that you can use that and apply it when it shows up in an expression that's a little bit crunchier or a little bit more involved than in just one as simple as 1 over cosine. So having said that, to give you an idea, the sort of identities that we're going to be looking at will look something like this. I'll change the color so we can see it better. You will, probably not in today's, but tomorrow's for sure, you'll run into identities that look like this. Or let's just call it, in this case, this isn't an identity, this is just an expression. You'll have an expression that looks like this, sine of x times cosecant of x. Your job will be to simplify it. And if you're going to go through and work this out, what's important is to realize that, oh, cosecant is really the same thing as the reciprocal of sine. And that means that those two divide away and make a 1, which gives us a value of 1. So we're going to be transforming trigonometric expressions into simpler ones by identifying and applying the fundamental identities that we'll hit today. So having said that, in addition to what I've just described as that simplifying process, there are actually 3 different ways that you might apply trig identities or work with trig identities in here. And we'll do a little bit of all 3 of these just at different levels based on the fact that, oh, I don't know, we're not able to go to school anymore because there's a nationwide pandemic, actually pretty much international pandemic. So having said that, the 3 things that you might be asked to do, first and foremost, you could be asked to prove identities. As I said, normally when I say proof to people start to get all panicky and like, oh, proof? No, I'm not going to prove. I'm not a mathematician. We're talking about like proving by, here's a triangle, label the sides. So, don't get too worried yet. We'll take care of that, and I'll demonstrate that for you too. Second, in addition to that, obviously what we said a second ago is true. We're going to simplify expressions. So in this case, what I mean is what we saw on the right side in that plum purple color. We're going to take expressions that have multiple crunchy trig identities there, and we'll try to apply the simpler ones to clean up the expression and get it to a point that's easier to work with. And then third, this last step, we're not going to do it intensely like you would in the normal course if we weren't stuck at home. But having said that, you can also verify identities. In a sense, verifying identities is just kind of like someone tells you what the expression simplifies to and then says, show me how I got there. So we'll probably do a little bit of that just because some of the problems are pretty interesting. And truthfully, I can give you the exact problems that you'll need to be prepared for calculus next year. So I might as well do that while I'm still here. Having said all that, obviously, as I pointed out at the very beginning, my goal today is just to expose you to what the fundamental identities are and give you a moment to just kind of see them in action in a very simple context. So I'm going to move pretty fast. I'm taking advantage of the fact that, of course, you can pause this at any point. If you feel like I'm talking too slow, well, that's too bad. I can talk even faster if you really want me to. Just kidding. If you want to speed things up, obviously, like I'm hoping I'll be able to upload this to YouTube and you can use the speed up features too. And obviously you can pick and choose your spots as well, but obviously I want to hit every single one of the types of fundamental identities out there and give you some strategies for remembering them as well, because typically you would be asked to memorize these things, and as a calculus teacher I can tell you that I would expect you to be able to recognize the most basic and most important ones that we'll see here. So without further ado, let's jump into the first one. So the first type of identity we're going to look at is called a reciprocal identity, and the reciprocal identities are a good place to start because truthfully you probably already know them. As it says, we have all the greatest hits of identities. Look at that. They're all the ways we defined what we literally call the reciprocal trig functions. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. Then 1 over is the same thing as just flipping it. Not sure if people have thought about this before, but if you have 1 over a ratio, that's the same thing as multiplying up and down or dividing by it. So lots of ways to get there. This becomes just b over a. So literally 1 over a fraction flips the fraction. So it's reciprocal just like it always has been. Excuse me. What you might not have realized is that, of course, because we don't normally go in that direction, that the reciprocal identities work in both directions as well. So if cosecant is 1 over sine, that means sine is 1 over cosecant. Cosine is 1 over secant, and tangent is 1 over cotangent. So having said that, these are the most familiar, so they're a really good place to begin. These building blocks are oftentimes going to be the only real tool we need to simplify an expression. But as I said, the real purpose here isn't to do anything really intense with it or any intense simplifying for today. I just want to kind of expose you to them and show you some ways in which you could use them. Not necessarily in a practical way, but kind of show you what's there. It's weird, that looked like an Oreo for a second. Okay, so down here below, I have our first example. And in case you're wondering, that symbol right there, that stands for ejemplo. That's example in Spanish. I choose EJ because EX has a particular meaning in math, so I wanted to clarify, and I just like doing it. Yeah, by the way, it's just fun to make that symbol. So that stands for an example. So it says, if secant of x is equal to 4/3, find cosine of x. Now, truthfully, we probably don't need to do any work for you to be able to get this. If you know the reciprocal relationship, you know that the answer is just going to be 3/4. Having said that, in truth, if you were less confident in that identity or in that relationship, where you would probably begin is actually fairly complicated. You'd take into account that secant is hypotenuse over adjacent. You do the Pythagorean theorem really fast. So 4 squared equals 3 squared plus the missing side squared. That means that the missing side squared is equal to 16 minus 9. And then you'd find that third side, and then you'd go figure out what the cosine is, and you'd go, well, that's equal to 3/4. Obviously, that's not the most practical way to get there, but it's the way that we probably kind of build up in our minds when we learn trig relationships right at the very beginning. Having said that, though, with this new approach in place, with this new identity approach, like for more complicated problems than this one at least, a good way to think about it would be instead this way. We know that cosine of x is equal to 1 over secant of x, presumably. Since we were told that secant was 4/3, this is equivalent to 1 over 4/3, which is equal to 3/4. And there is our answer. So in a sense, the identity gives us a pathway to follow things through and get to our answer really quickly. Now, having said that, in practical terms, if you're going to do this, just flip it in your head when you know the reciprocal relationship and jump right in. But having said that, this is kind of the approach we're highlighting. These relationships will save us a little bit of trouble. We definitely don't need to draw a triangle when we have a relationship that connects those two automatically. So there are the reciprocal identities. The next ones we're going to look at are the quotient identities, and I think these are two that you may have run into already, but maybe you just haven't really thought about before. And they involve the definitions for tangent and cotangent. And it's weird for me because, in my mind, I feel like these are so fundamental at this point, but that's because I've been using them since 2002. So it's just been a longer, 18 years. Wow, over half my life I've been using trig identities. It's a weird thought, sobering thought. Having said that, when we take a look here, these two quotient identities, that tangent of theta equals sine over cosine, and that cotangent is equal to cosine over sine, are both relationships that are really fundamental and that we can really take advantage of. So first and foremost, what I'm going to do is, as it says right here, it says PF. The PF stands for proof. So we're going to do a quick little proof here. So just to kind of show you, and before you turn it off or start groaning and oh, this guy and his proofs, let me just show you what I mean. We're going to label this triangle with the side lengths x, y, and r. So far, so good. Not every proof begins this cleanly. But from here, let's start with determining what sine of theta and cosine of theta are equal to. Well, from the picture, sine, which is opposite over hypotenuse, that's so in SOHCAHTOA, opposite over hypotenuse is going to be y divided by r. Likewise, cosine of theta is going to be adjacent over hypotenuse, which is going to be x over r. So there's the beginning of our stuff. We're just defining what sine and cosine are. Now let's take a look. Sine of theta divided by cosine of theta, so we'll focus on the tangent one, is going to be equal to sine over cosine. So far, so good. From here, since we're dividing by fractions, however you think about it, this will be y over r divided by x over r. But we know that when you divide fractions, you can multiply by the reciprocal of the second one. So from here, we get y over r times r over x. The r's divide out, and we're left with y over x. And then from here, if we look, y over x is opposite over adjacent, which is equal to tangent of theta. So what we've just shown, so therefore, those three dots mean therefore, probably run into them before, therefore, sine of theta over cosine of theta is equal to tangent of theta. And since we did a nice formal proof, we can put a little QED at the end. Another thing that's just kind of showing off mathematically to say, ha, I did it. It stands for quote erat demonstratum. That which has been proven is there. So again, these two relationships, like another very fundamental ones, these show up very often, and in fact they're a huge part of some of the trig identity work that pops up occasionally in calculus. We can definitely take advantage of tangent being written as sine and cosine, because we'll know more about sine and cosine as functions than tangent. But as far as examples go, we can take a look at how this could save us a little bit of time. So in our example right here, we're told that cosine of theta is 5/13 and sine of theta is 12/13. They want us to find cotangent of theta. Now again, if we think this through the old-fashioned way, we could go backwards and we could draw a triangle out and then label things and then figure it out from there. But we don't actually have to do that anymore. Let's take advantage of the fact that we've just established this quotient identity, which says cotangent of theta is equal to cosine of theta over sine of theta. Having done that, we can make our substitution. It says cosine is 5/13, and it says sine is 12/13. From there, doing our same piece, we get 5/13 times the reciprocal 13/12. The 13s undo one another, and that leaves us with 5/12. So we now know the cotangent of theta, given that information that's right up there. So again, for today, quotient identity, fairly important. I'd say that this was probably a little more new, feeling a little more new to you than the original reciprocal identities, but definitely a very straightforward one to work with. So there's our second set of identities. The next set of identities we're going to look at are the ones that you're seeing right here, and although you may be thinking you need to head to an optometrist at some point when this is all over, because you might be seeing triple here. The truth is there are actually three of what we call the Pythagorean identities. There are three separate sets involving different pairs of trigonometric ratios. Having said that, though, I want to focus on the first one primarily right now, and then I'll use it to build out the other ones. Because again, our goal ultimately is that you know these identities and can recognize them and figure out moments when it's helpful to change from one expression to the other. So let's make sure that we have ways for you to remember them. And I've got a couple different tricks up my sleeve. One of them from Miss Williams that a couple of my BC students shared with me this year. So having said that, the first thing I want to point out is as you look at these identities, if you're looking at it and not thinking that there's a whole lot Pythagorean about it, let me rewrite it first this way. Think of this as sine squared plus cosine squared equals 1 squared. So in a sense, it's the sum of two squares equals something else squared. So there has to be some sort of a squared plus b squared equals c squared relationship happening here. Second, because sometimes people don't recognize this, and I think it's really fundamental here, when you see an expression like this, cosine squared of theta, it's important to remind ourselves that that's equivalent to cosine of theta squared. It means the exact same thing. It's just squaring cosine. It's just mathematicians like to make things really short and efficient, so they bring the 2 on the inside. In fact, some places will actually do function notation that way. They'll say this, f squared of x is the same thing as f of x squared. Now, thankfully, that notation is not as common anymore, but there are situations where it pops up. So just know that that's the same thing as saying cosine times cosine, just written in a very clean way. So having said that, before I look at where other Pythagorean identities come from, let me first point out that this is the biggest, most important, most common one. We run into this all the time. In fact, it's a favorite trick of mine when I write the harder standard quizzes in calculus. Oftentimes we'll put in sine squared plus cosine squared because it looks intimidating, but it's actually just equal to 1. So it's really simple to work with. Now let me point out that this particular Pythagorean identity here, sine squared plus cosine squared equals 1, often shows up in 2 other different packages. It just kind of depends on what's there. One of those packages would be to isolate the sine squared and say that sine squared is equal to 1 minus cosine squared. The other one is completely analogous or parallel. It's isolating cosine squared and letting cosine squared be equal to, 1 minus sine squared of theta. So these are all the same one. These are kind of the principal Pythagorean identity. They're the most common one. Having said that though, this is the only one where truthfully I ever really have memorized this relationship. Although I'll give you some tools to memorize the other one. Instead, when I look at the other ones, I tend to just think about their relationship to this first Pythagorean identity. Because in my mind, it's easy to remember one thing and then how to go from that one thing to something else much more easily, there's probably the right way to say it, much more easily than it is to just memorize a bunch of stuff. Because I forget things. I have lots of stuffs in my head. It's easy to forget things over the course of time. So for these other ones, I'm going to show you how to derive these other identities. So we're going to derive them. Not like hop in the car, turn in the ignition, and then, go for a cruise. That would be driving them. We're going to derive them. Had to make a pun at some point. So the approach that we're going to take to derive these other versions of the Pythagorean identities, and I'll give you a rundown on the next page, the process is going to be basically how we can transform an expression that has sines and cosines and a 1 into an expression that has, say, tangents. And in fact, I'll make that my goal on the first part here. I'm going to divide this entire expression. In fact, I should do it on both sides. I'm going to divide this entire expression on both sides by sine squared. In fact, I called it an expression. I apologize. It's an equation. Divide the entire equation on both sides by sine squared. Now, when we do that, what does that accomplish? Well, first of all, it looks like on the right side, we've got that cleaned up quite a bit. The right side is 1 over sine squared. That's the same thing, by the way, as 1 over sine of theta times 1 over sine of theta. So I'm hoping it's okay with you that I just say that 1 over sine times 1 over sine is the same thing as cosecant squared of theta. But even before we get there, we've got that left side. And what I'm going to do is I'm going to separate it into two separate parts. I'm going to separate this into sine squared of theta over sine squared of theta. And then I'll add to it, of course, cosine squared of theta divided by sine squared of theta. So now having done that, obviously we now have done the same thing on both sides, so this equation is just as valid as the first one was. But the nice thing is this cleans itself up really, really nicely. Like, take a look at the first thing. We already mentioned the 1 over sine squared becoming cosecant squared. Sine squared over sine squared is just equal to 1. The next one is cosine over sine, and yeah, it's squared, but cosine over sine is a reciprocal identity, and we recognize that that one's equal to cotangent. So this must be equal to cotangent squared. And then, of course, we already said that cosecant squared is what's right up there. And this is our second one of those identities. This is a second Pythagorean identity that relates the squares of cotangent and cosecant. So it's like the special one that's out there. So in fact, if you're looking for a way to remember this, this isn't my own way. I'm taking this from Miss Williams. A bunch of my students who had her for Math 2 and Accelerated Math 3 that were in BC shared this with me. They point out that Miss Williams always tells them, I collect seashells. And that gives you the proper order. Obviously, you still have to remember what the where the equal sign falls, but I collect seashells is a great way to remember that. It fits really nicely. And in fact, it sticks with the theme of the beach, things that we can't do right now because they're all, I think, closed down in California. But we can do the same kind of approach and get a second, or a third version in this case, of the Pythagorean identity by, instead of dividing by sine squared like we did on the red one, we're going to divide both sides by cosine squared. I just need to fix that fraction bar because that made me very, very sad to see that poor line. So I'm going to divide both sides by cosine squared of theta. So when I do that, just like I did before, I'll keep my work parallel. The first term will become sine squared over cosine squared. The second term will be cosine squared over cosine squared. We can appreciate that a little bit. That works out really nicely. And then the last one is, of course, 1 over cosine squared. Well, some of these simplify a little easier than others. So obviously we have plus 1 because cosine over cosine is going to go to 1 because they're the same thing. Divided by the same thing, you get 1. The first one is sine over cosine, yes, squared, but sine over cosine is a reciprocal identity. This is in fact going to be tangent squared of theta. And then on the far right side, 1 over cosine, we already talked about that. That is equal to secant, so this is secant squared. So this is a second Pythagorean identity. Truthfully, this is kind of the way that I've known it the most, but something that, again, comes from Mrs. Williams is if you want to, you could rearrange this so that it resembles the earlier one in red and write it as 1 plus tangent squared is equal to secant squared. And the reason I bring this one up is that if you like this, I collect seashells, memorization or mnemonic technique, this one fits really well. I tan by the sea, which is definitely true. Like, you definitely need sunscreen when you're by the sea because typically there's a sun out and typically many of us burn. So again, I collect seashells and I tan by the sea are good ways to remember those if you want to memorize them. It's not my way, but hey, you be you. So having said that, in culmination, this gives us all of our Pythagorean identities, kind of in all their different forms. So I've written them in kind of all the reasonable ways that you're going to run into. Truthfully, you could probably write these other ones one other way as well, but I'm just going to leave them right there. So again, the key ones, the ones that are like the ones you kind of want to know and that will show up most frequently, whether you memorize them or not, are sine squared plus cosine squared equals 1. That's the one you really got to know. The second one is I tan by the c, or tangent squared plus 1 equals secant squared. And then finally, 1 plus cotangent squared equals cosecant squared, or I collect seashells. Let me just point one more thing out before we go forward, or before I prove this. I think that's all I'm going to do is just prove something here. Let me just point out to you that a lot of people see this and they think, oh, cool, that means 1 plus cotangent equals cosecant. Yay! No, not a thing. That's not a relationship. This relationship is specifically for squares. So it's the squares of these things work, not the original values. Not sine. You can't change this first one to sine plus cosine equals 1 because it's not gonna. It might work that way. It will not. Well, no, it won't work that way at all. So make sure that you don't fall into that trap. This only works for squares. So only squared versions. I'll call them only squared trigs. Triggies. That's a fun one. Triggies. Trig functions. We'll call them triggies. So there we go. Okay, so having seen these things, I do want to point out and just kind of take one moment just to prove the Pythagorean identity, because this is very likely to be one that you have not run into before. It doesn't just come up serendipitously. You aren't just walking along like, oh, look, a Pythagorean identity. How quaint. So instead, let's just kind of prove and make sure that this actually works. And I'm going to focus on the classic sine squared plus cosine squared equals 1, although this would work with any of the three main trig identities or any version of their forms. So to kick this off, let's start in the straightforward place. We want to figure out what sine is equal to and what cosine is equal to. Before I can do that, though, I need to label the sides of the triangle. And I'm going to go ahead and label the horizontal x, the vertical y, and the diagonal or hypotenuse r. Those are pretty standard ways of labeling them, specifically because x is horizontal, y is vertical, and r looks like a radius of the unit circle or something. So having said that, having established that, we can go ahead and point out our values of sine and cosine. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. From here, the next thing we want to do is we want to set up a relationship that holds for this entire triangle. So based on the fact that it's a right triangle, not a left triangle, not a wrong triangle, but a right triangle, because of that, we know that x squared plus y squared has to equal r squared, right? That's a given, like it's definitely true. That's just the Pythagorean theorem. I guess I'll write that in there, the Pythagorean theorem. So by knowing the Pythagorean theorem, that's an important place to begin. From here, though, what I'm going to do is I'm going to make a move. I'm going to do something that we've done a couple times already. I'm going to divide both sides of this equation by r squared. When I do, I can break this up into x squared over r squared plus y squared over r squared. And then all of that's going to be equal to 1. That's a good sign because this Pythagorean identity is equal to 1. On the left, though, we have x over r, or x squared over r squared. I'm going to rewrite that as x over r squared. And I'll do the same thing with y squared over r squared. I'll rewrite it as y over r squared. And of course, this all remains equal to 1. But here's kind of the cool thing. We said earlier, sine of theta is y over r, and cosine of theta is x over r. So having done that, we can replace these pieces and point out that this first one is going to be cosine of theta squared, and the second one is going to be sine of theta squared. It's all equal to 1. And then the last move would just be to clean this up and put it back in the order we expect. So I'll rewrite this final step using, I think it's called commutativity, the commutative property. I can rewrite this as sine squared plus cosine squared is equal to 1. And hey, that was exactly what we were trying to do in the first place. Bravo. So in any event, there are the Pythagorean identities. You've seen the identities themselves. You've gotten some mnemonic devices, courtesy of Miss Williams, as told by me. And then you've got a couple pieces of information that show you how you can get there if you're not into memorizing like me. So having said that, like there are the Pythagorean identities. But of course, rather than spend time doing an example with the Pythagorean identities, I want to just wrap this up. So I'm going to go ahead and go on to the next type of identity. If you're offended by that, well, take it up with your computer screen, I guess. Yeah. Alrighty, that brings us to our second to last of the fundamental trig identities, and these are called cofunction identities. And although these identities are, again, probably not ones that you've run into very extensively, the truth is these are kind of nice because they offer some explanation of why that prefix co shows up in some of the names. Like, why is there a cosecant or a cotangent? Like, how does that relationship come together? The answer is actually right here. So I don't have these expressions like the other half of this expression, or what it simplifies into. But the first one, sine of pi over 2 minus theta, is equal to cosine of theta. And cosine of pi over 2 minus theta is equal to sine of theta. So I'm hoping what you notice there is sine of this is equal to cosine, and cosine of this thing is equal to sine. So sine and cosine are kind of a cofunction pair. It's a good way to look at it. Predictably then, tangent of pi over 2 minus theta is equal to cotangent of theta, and cotangent of pi over 2 minus theta is, yeah, you guessed it, it's tangent of theta. And of course, secant and cosecant follow the exact same pattern. It's pretty cool. I was going for co and cool, but I'm not sure if it worked. In any event, well, I can't tell. So right up here, these are the cofunction identities. I find them easy to remember because that's kind of what gave me, I'll call it an explanation for the naming system. Like, why do we call it cosine? Why not give it the name like Gurgulf? Like sine and Gurgulf. Like, why call it cosine? Like, why have them attached to each other with sine? And the answer is this relationship. And the truth is, this can be very awkward looking. It looks much more complicated than it is. So I think the proof here is really essential to get this idea into your head. So first and foremost, what I want to point out in our triangle is, of course, if we're going to work with it, we need to label it. But we've been pretty comfortable labeling this as x, y, and r, respectively. So starting there, what we want to do is let's start with something simple. Like, I'm trying to pick out which one that I proved before. Yeah, we'll just go this way. We want to figure out what is the cosine of pi over 2 minus theta. And remember, pi over 2 radians is the same thing as 90 degrees. So just kind of keep that in the back of your head too. I think that helps a little bit. Obviously, it's been a little while since you worked with radians, although probably not that radian. I don't know what time it is. So from here, if we want to try to figure out what the cosine of this angle pi over 2 minus theta is, we need to think about where in the triangle it could actually be. This is theta, and this angle is 90 degrees, or pi over 2 radians. What that means is that we can actually figure out what this angle's measurement would be relative to those other two things. Specifically up here, this thing that I typically think of as the other angle, so as though it's somehow like less than, it's some other angle, so the other one's the special one. But in a sense, the reason this other angle is up there is we know it has to be the complement of the angle in the lower left corner. It's got to be the complement of this guy, meaning that those two add up to 90, which means that it's equal to either 90 degrees minus theta, or more likely, since we're going to be using radians presumably, it's going to be pi over 2 minus theta. So in a sense, what we've just shown is that that angle right in here, this guy right there, making the little dot, I don't know why my voice went up, but it's there, that angle is pi over 2 minus theta. And what that means is if we want to figure out what the cosine of pi over 2 minus theta is, we just need to take the cosine of that other angle. And I'll label angle that way. So cosine of that other angle is going to be, let's see, adjacent for this guy is going to be y. And hypotenuse is, well, the same hypotenuse. So it's y over r. Oops, erased it all. So cosine of that other angle is y over r. Now from here, to finish this off, we just need to know what other trig ratio has the ratio y over r. Well, relative to theta, we have opposite and hypotenuse, which means y over r is equal to sine of theta. And that means, as our identities up there told us, the cosine of pi over 2 minus theta is just equal to the sine of theta. So in fact, there it is. It is indeed that relationship. Cofunction is kind of with the other function. It's like it goes along with that other angle. So anytime you're asked about a cofunction, if you want to kind of ground it into something concrete, sketch a triangle and just think about it as the other angle that we didn't label, and the relationship will show itself just the same way as these trig identity ones do themselves. So again, I'd say that at first these can be kind of intimidating. Hopefully that little discussion about the naming, like the nomenclature, ooh, I sound fancy when I say it, the nomenclature of the sine, cosine, these trig ratios helps you remember the cofunction identities, because otherwise they definitely do look intimidating. I can't deny that, but I don't think they're anything you can't handle. The last ones we want to hit are the even and odd identities, and these are written in here. Like I have them already pasted in there, so sorry they're a little bit smaller. And I'm actually going to prove 2 of them for you as kind of our final piece of this short little introduction, simply so that you can kind of see them occurring 2 different ways. So in here, something that's important to note is I've paired them up. So sine and cosecant go together, cosine and secant go together, and tangent and cotangent go together. So in other words, what I've done is I've paired the reciprocal functions together. Because the reciprocals only differ by 1 over, they're just like a difference of flipping the thing, so the sign's going to stay the same on each of those. So the way these relationships go is that sine and cosecant, if you plug in a negative angle, give you the negative of the ratio. Same thing is true for tangent and cotangent. And if you're ever curious why it is that tangent and cotangent maintain it, it has to do with the reciprocal, not the reciprocal, excuse me, it has to do with the quotient identity, because you have a sine and a cosine both in there. Cosine, on the other hand, and secant, its reciprocal, are the ones that stay positive, or they become positive. Like in a sense, it's like the negative angle isn't even there. And that begs the question, why is it that that works out that way? Like, how is it that that's going on? Like, what's going on that makes cosine stay positive or keep its sign, but sine and tangent and their reciprocals suddenly change to negative? And the answer comes in doing a little bit of a proof. So what I'm going to do is, just like always, I'm going to start by, well, it looks like I've already began because something was left in there from when I taught it in 2018. So what I'm going to do is, in our little triangle picture, I'm going to start by labeling the sides. I'm going to call this x, y, and r, no differently. And that is all relative to angle theta. Now, our question, though, has to do with these identities that feature things like sine of negative theta or cotangent of negative theta. So if that's theta, negative theta has to be right down here. Okay, I may have drawn that a little awkwardly. There we go. So if that's theta up top, then this would be negative theta. As far as labeling the side lengths, x is the exact same length that it was before. Y, though, has flipped. So y becomes negative y, or that opposite side of the triangle, it's a better way to put it. The opposite side becomes negative y. And then r is the hypotenuse, which we always consider positive anyway. So having done that, we now have our triangle labeled. The question that we want to ask is, of course, what is the sign of, say, negative theta? Because that's what these even-odd identities are talking about. The answer is, well, let's just read it off the picture. According to the picture, sine of negative theta is opposite over hypotenuse. That's going to be equal to negative y over r. So having said that, if I rewrite this in a slightly leading way, I can rewrite this as negative times y over r. And of course, the reason why I did it in this way is because y over r happens to be sine of theta. So in other words, just by working through that, we can see that on regular theta, positive theta, we get y over r as our opposite and hypotenuse, which means exactly what we expected, or at least exactly what the Trig Identities info up top said. Sine of negative theta is equal to negative sine of theta. So if I had to give you an explanation for why it is that sine actually changes, it's because negative theta is going to have that flipping, that reflecting behavior, and that's going to change the sign no matter where your original angle fell. It's going to change the sign of your height, and sine, of course, corresponds to the height, something you've run into before in probably the graphing unit as well. Now, having said that, that answers the sine question, and we could do, of course, the proof for cosecant or tangent or any of those as well. But I'd like to investigate really quickly as kind of our last little piece, why is it that cosine doesn't change if this thing's flipping? Well, to kick things off, let me draw in our triangle here. It's not quite perfectly symmetrical, but we'll live. There's negative theta. If we label the sides, just as before, x, y, and r, then following this pattern, of course, leaves the sides labeled x, negative y, though, and r. So our question in this piece is, what is, say, the cosine of negative theta? Because we've been led to believe it's going to stay positive. Well, looking at the cosine of negative theta, we're going to use adjacent over hypotenuse. Adjacent is x, hypotenuse is r. Well, there's no negative sign there at all, and looking up at our picture, adjacent and hypotenuse both happen to be x and r for positive theta, which means the cosine of negative theta is actually the exact same thing as the cosine of theta. So in other words, we've just demonstrated another even-odd identity. As far as explanations for why, it's kind of that reflective behavior is specifically across the x-axis. So the horizontal relationship, whether it's positive or negative, isn't actually changing here. It's the exact same length. In fact, we can see from our picture that it's literally the same length. It's that same segment that's forming the adjacent side for positive theta as it is for negative theta. So the truth is cosine, and of course it's reciprocal, don't use that reflected vertical height. So in other words, they just maintain the sign that they had originally. And those are the even and odd identities. And again, I think that just kind of having some comfort with where this comes from obviously gives you a backup tool in case you forget which ones are positive and which ones are negative. But I think it's also just, it gives you a little more ammunition if you're going to memorize these to kind of remember, oh yeah, cosine's there, horizontal, okay, cool, we have it. So having said that, that brings to a conclusion this kind of introduction to trig identities. Just kind of went through all the fundamental ones that are out there. As kind of a means of a quick review of what we did, we talked about what an identity was with some basic trig ones and some other relationships that we already knew. From there, we talked about the fundamental identities and kind of what our goal was. So our roadmap is that we wanted to start by just kind of proving the identities and then simplifying some trig expressions. We didn't really get there, but we're going to do that in the next lesson. Maybe do a little verifying. And then from there, we talked about all the identities. Talked about the reciprocal ones that you pretty much already knew, although maybe not necessarily had thought of them in both directions the same way. Gave you a very clean example you probably could have done in your head. Then we talked about the quotient identities. We proved it, in fact, for the first time. We showed you a place where you could use it. We talked about the Pythagorean identity, and in fact, we were able to derive the other two Pythagorean identities. And I showed the mnemonic device from Miss Williams. That's I tan by the sea and I collect seashells, if you want to memorize them instead of deriving them each time or kind of using that as a tool. We then proved that and emphasized, by the way, that the Pythagorean identities only work for squares. That's why they're called Pythagorean. And then from there we talked about the cofunction identities and that other angle that we tend to kind of dismiss, but in fact opens up the entire world for the entire naming system that we use for trig functions. And then finally, last but not least, we talked about the even and odd identities, and we showed you why it is that 4 of them end up giving you a negative sign, and 2 of them end up staying positive or maintaining their same sign. So having said that, obviously I haven't gotten to be your teacher this year. You've had great teachers already, but hopefully this was a nice little help to offer you some insight into a new topic that we're going to briefly study here as you're working through distance learning this year. Nothing else that I need to say. So until the next lesson, when we talk about simplifying and maybe even doing some verifying with identities, thank you for watching and have a great night.